So I'd like to proceed and introduce our first speaker for the next session. So Lucia. So the title of her presentation is Aluminium Innovation for EV Chassis Component Hybrid Solutions developed in the Fatigue4Light project. And I'd like to say a few words about Lucia in terms of her background. So Lucia is an assistant professor at the Polytechnic University of Catalonia and an assistant research professor at the International Center for Numerical Methods Engineering in CIMNE in Barcelona, Spain. So currently she's leading the research unit on constitutive modeling of nonlinear processes with a special focus on fatigue. So please, Lucia, you have the floor.
Thank you so much. Thank you for the kind presentation. I hope I shared my screen. Yeah, I did. Okay, so from my side, today I'm representing the Fatigue4Light project, even though we have these technical difficulties. We are dealing in the Fatigue4Light project with fatigue modeling, some fast testing methodologies, because we want to optimize part design and to boost lightweight material deployment on chassis parts. And specifically in my talk today, I want to focus it or to highlight the aluminum innovation that we had on electric vehicle chassis components through the hybrid solutions that we developed in the Fatigue4Light project. And regarding my talk today, it's structured in such a way in which I will begin explaining by what is the general overview of our project and our consortium. I will share with you very briefly the project phases and what is the research beyond the state of the art that we are pursuing in the project. Then I will speak about what are the materials that we are focused on analyzing in the Fatigue4Light project. And I will finish with a very brief overview, because of the time, on the results that we've been achieving in the project at material level, lab scale demonstrator, and also industrial demonstrator. Okay, so now I'm going to go to the slide on the Fatigue4Light general overview. And just to give you some information about our project, it's a 3-year duration project funded under the Horizon 2020 program. We are close to the end of the time for our project. We are finishing the work because we are going to end the project at the end of January, 2024. And we've been funded with 5 million euros by the European Commission. We are 13 different partners from 4 different European countries. And the coordinator is CIMNE, which is the International Center for Numerical Methods in Engineering here in Barcelona, Spain, which I'm representing today. Okay, now an overview on our consortium. We have 4 different types of partners here. We are 3 research institutions, which are CIMNE, EURECAT, and RISE. We have 3 universities involved, Lucia University, Politecnico di Torino, and the Polytechnic University of Catalonia, UPC. Also, we have 6 industrial companies. We have Fiat, CRF, Magneto Wheels, ArcelorMittal, Gestamp, Hardtech, Profil Glass, which is an aluminum supplier, and Composite Service Europe. And we have 1 standardization body to help us with standardization issues, which is UNE. Okay, now, if I want to humanize a little bit our consortium, here you can see the evolution we've had through the years while we were working on the Fatigue4Light project, going from the online, let's say, meeting mode into the in-person meeting mode, finally after the COVID pandemic. And you can see that we've only grown more beautiful with the years, not any fatter, not any white hairs, just wiser and more beautiful, okay? Now, regarding the project phases in the Fatigue4Light, the project is structured in such a way that we devoted the first year of the project to studying the material behavior at coupon scale. After that, we went to a lab scale demonstrator where we focused our effort in the second year of the project. And now in the 3rd year, we are intensely focused on analyzing the behavior at component level at industrial demonstrator. And in the project, we followed such a timeline that we began by studying the performance, the mechanical and also the environmental performance of different types of steel, also aluminium, also multi-material hybrid solutions. After that, we dedicated a lot of effort to developing experimental tools for lightweighting. And specifically, our project is very, very focused on fatigue, so behavior under cyclic loading. And I don't know if you're aware of this, but a fatigue testing campaign, for instance, is a very lengthy and costly procedure. So if you can develop new experimental tests that can help you save time and save money, that is a very big added value for all the industries, I would say, where fatigue is a problem, obviously for the automotive industry also. After that, we again set up to work on computer and simulation methods, specifically oriented, let's say, to better estimating the fatigue life of chassis components. And with these tools helping us to select the optimal materials for lighter chassis components. And then we wanted to bring all of these different building blocks, I would say, that we developed in the project to a component scale and validating the solutions developed at lab scale and industrial scale. Okay, next, just to speak about the research beyond the state of the art. Here, the focus in our project was developing a fatigue computer simulation method, which was comprehensive in the sense that it took into account all of those nonlinear effects induced by the manufacturing processes. And here I mean manufacturing processes such as cold stamping, hot stamping, punching, cutting, forming, welding. All of these processes, they induce specific effects on the materials, which later on affect their performance under specific loadings, as for instance, the fatigue modeling. So in our case, we wanted to have this approach where we followed the performance of the material from the sheets until the final components which were being tested. Now, what are the materials that we analyzed in the Fatigue4Light project? Well, we devoted some effort on analyzing the behavior of advanced high-strength steels. And here we've been dealing with CP800 for some application where it is not current state of the art, and CP980, 1000 for other applications. Then we wanted to also study the behavior of stainless steels and also some hybrid solutions which were built with aluminium alloys and also with glass fiber reinforced polymers and carbon fiber reinforced polymers. We've also studied press hardening steels, advanced boron steels for press hardening of thick sheets, and of course the behavior of aluminium alloys, which have improved fatigue resistance, reduced cost, and improved environmental profile, of course, thanks to the high amount of scrap. Okay, now since you are seeing the PDF version of my presentation, you'll be missing all of the animations that I have developed for the presentation today, but it's okay. Some results at material level. In our project during the first year, we had a very extensive experimental campaign where we studied 4 different types of behavior. Of course, the tensile performance of our materials, local formability test, fracture toughness, and also environmental effects through some corrosion tests that we performed. And since it's a brief overview that I can share with you today, I just wanted to share some results in which you can see comparatively the performance under these 4 different types of tests. However, for our project, the most important result I would say that we were interested in finding out was the fatigue performance. So in this sense, we've analyzed the material studied in the project through several different perspectives on fatigue, with the conventional staircase method, also with some very new methods, which are fast fatigue testing methods, the self-heating method, which was a method proposed by ArcelorMittal, and the stiffness method, which was a method proposed by Eurecat. And also we analyzed the performance of these materials under very high cycle fatigue domain, an analysis done by Politecnico di Torino, our partner. And here you can see a brief overview where we tried to rank the performance of the different materials by dividing their fatigue strength with the mass and for a specific reversion factor, 0.1. And what I want to spend some time on is on explaining to you one of the fast fatigue experimental approaches developed in the project, which is the stiffness method proposed by EURECAT. And this is a very interesting approach because here, for instance, with only 3 hourglass specimens and in about 4 hours, you can already get a very good approximation, actually, of the fatigue limit of a specific material. And how is this test performed? Basically, we will be applying, or we are applying, blocks of 6,000 cycles of loading with increasing levels of amplitude. And after each block, we measure the stiffness of the material. So we unload the material and we measure what is the stiffness response. And when we detect a change in this stiffness is when we can say that we have located the fatigue limit of the material. And what's interesting also about this approach is that you can find the fatigue limit affected by several different manufacturing processes, for instance, such as trimming and punching, forming and corrosion, etc. And you can see here a paper published on this test if you want to know more information specifically. Okay, now regarding the results at lab scale demonstrator level, we devised a specific geometry which was of interest for us, which had some bending and some punched holes and some trimming involved. And this industrial demonstrator was tested at EURECAT facilities in their laboratory. And we wanted to look at the comparison between the performance of fully polished configuration with a half polished configuration to understand the influence of the surface, I would say, finishing on the fatigue behavior. From CIMNE's side, from my institution, we performed a numerical analysis campaign. And then we saw if with the fatigue approach, numerical approach simulation that we have, we approximate correctly the behavior observed experimentally. And here you can see that we do. There was a small animation here, but unfortunately you will not be able to see it with the crack propagation at a bit past 1 million cycles for the CP800 still. Okay. If I go to results at demonstrator level, now I have a lot of information on this slide, so I'm going to go one by one explaining what we can see here. First, we can have overview of 2 different demonstrators that we developed in the project. Both of them are for a lower control arm, okay, on a Fiat car, and we studied this demonstrator from several different perspectives. One was to produce it, to manufacture, test, and model with a still version with the CP980. Okay, so complex phase 1000, let's say. Fiat, the CRF, manufactured this low control arm and tested it. And you can see here in the third image what is the final result after the testing with the failure of the specimen, some buckling that occurred on the inner side of the low control arm. And after that, ideally, you would have been able to see some simulations which were performed by CRF at system level and by CIMNE at component level, where you can see the failure mode. This time this is the misuse test, so it's just monotonic loading, and the fatigue testing is currently underway, let's say. Then on the lower part of the slide, we have the same demonstrator envisioned, so the lower control arm, but this time we want to model its performance with a hybrid version. So a hybrid version, which means that we have 2 aluminum sheets, 0.8 thickness on the outer parts of the demonstrator. And in the middle, we have a core with glass fiber reinforced polymer, 1.6 millimeter thickness. And this demonstrator was developed at RISE, manufactured and tested at RISE. And ideally, you could have seen here a video of the test. I had a lot of videos for today, but well, it is what it is. And then from CIMNE's side, we modeled this hybrid version of the lower control arm, and we checked to see if we obtained a good performance. Still, this is just monotonic testing. As I said, fatigue testing is next steps, let's say, what is left in the project. Okay, now I would like to show you, I would have liked to show you a nice video where you see the stamping of this hybrid lower control arm performed at RISE. In the PDF version, you won't be able to see it, but I put the link over there below. So if you go to YouTube, you can have a really nice experience for about 1.5 minutes where you can see how we studied this hybrid lower control arm. First, with a numerical analysis campaign to decide what was the best geometry and do some topological optimization. And after that, with the actual manufacturing process of first stamping and forming the aluminum sheets and then joining together with the glass fiber reinforced core and how the final demonstrator was actually manufactured. I'm going to go forward. Okay, and then we have two different demonstrators that were also analyzed in our project. First, the wheel, we wanted to analyze the performance of a wheel, mainly the disc of the wheel, which was a demonstrator proposed by one of our partners, Magneto Wheels. They designed a new stamping cycle for trying out different materials studied in the project and seeing their performance on this demonstrator. And what was interesting to observe here is that, for instance, we saw that with the same stamping cycle, different materials have different performances after this forming cycle. For instance, for some of them, for some materials, the forming process induces beneficial effects towards the fatigue behavior, while for some other materials, the stamping cycle induces detrimental effects. So it's a very interesting result, I would say. After that, Magneto Wheels performed a quite extensive experimental campaign. They did a lot of work here when they studied the bending test on the discs for different materials with different types of treatment, with shot pinning, without shot pinning. And on CIMNE side, we also modeled these solutions to see if we were obtaining a good approximation of the fatigue life with respect to the experimental life, which I can also advance that we did. On the other hand, we had another demonstrator which we wanted to study in the project, which was a cross-member beam, which was proposed by our Swedish partner Gestamp Hartec. And they chose a symmetrical design. Here, I also had a nice animation where you could see the actual manufacturing process with the hot stamping of this cross-member beam. But either way, you can see the final result after the manufacturing. So they manufactured half a beam. And you can see the test setup where the beam was screwed to a plate. And then the cyclic loading, first the monotonic loading, but afterwards cyclic loading, was applied to the end of the beam in several directions to study the performance of this demonstrator, which was manufactured with the press hardened steel with 22 manganese boron 5. From CIMNE side, we also wanted to study the performance numerically. And at the moment, at least for the monotonic case, we are obtaining quite interesting, good approximation to what was seen in the test. Okay, now let me go forward. What about the eco-design assessment? Because what I've shown today is a lot of work that we've done in the project, but focused mainly on mechanical testing, right? So what was the mechanical performance of these different solutions? That's interesting, but that's not the only considerant that we want to have into mind when we rank performance for different materials, for different components. And we did a lot of work on the eco-design assessment. Now, today, the time that I have is limited, so I won't be able to share with you these results. So that's why to be continued. But I would really, really like to invite you to follow us if you are interested in these results that I've shown to you today on LinkedIn, on Twitter, on our YouTube channel, and also visit our website. And most importantly, we will be organizing quite a lot of webinars towards the end of the project where we want to share with the community our results and our findings. So if you're interested in this eco-design assessment, please join our webinars. We are waiting for you. And from my side, nothing else. Thank you very much for listening to me. And I terribly apologize for this this trouble with the animations in the presentation. Thank you.